Welcome to Empowered Learning. This video will serve as a very light introduction to differential equations, specifically ordinary differential equations. And so normally you'll see something like this pop up in, let's say, a Calculus 2 or Calculus B course where they're wanting to give you just a little flavor of what differential equations are before they kind of move on and talk about other things like integration techniques. And so part of the reason why in courses like that you'll see this light introduction is because most people, after they take Calculus 2 or Cal B, they will have all the basic tools necessary to be able to take an ordinary differential equations course, like the introduction to ordinary differential equations. So the examples I'm going to do here is very much like introductory type stuff, but it does coincide with what you would normally see in a traditional calculus textbook, because normally they separate the subject of differential equations versus calculus. So even though differential equations is calculus, it's just the calculus where your answers end up being equations instead of just values. So anyway, so the first thing that we want to do in this light introduction to differential equations is we want to make sure that we know what a differential equation is and how to check to see if a function is a viable solution for it. So in short, a differential equation is just an equation that has at least one derivative in at least one term in the equation. That's pretty much what it is. So the thing is let's say if you have terms that have a second derivative in it, then it's called a second order differential equation. If you have the highest derivative that you have is a third derivative, then it'll be a third order differential equation. Okay. Mainly in the introduction, we deal with just first order to make it easy. And so that's what we have here. So we have this differential equation 3 times the first derivative of y plus 5y is equal to 2 times e to the minus x. And we want to see if the following functions I have listed here are actually solutions for it. Now, just like how you did in algebra, to check to see if a function is a solution, you just substitute the function in and see does the left side equal the right side. Okay. The only thing that's different here is that because this term has the first derivative, we're going to actually have to find out what the first derivative of e raised to the minus x is first, because we need to use that too. So the derivative of e to the minus x is just a minus e to the minus x. And of course, we could get that by using the chain rule. But now that we have that, then we can come here and just substitute in. So we'll have 3 times a minus e to the minus x plus 5 times our original function here. And we want to see, does that equal to 2e to the minus x? And so here, this minus that's here, if we take the minus e to the minus x and multiply it times 3, we'll get a negative 3e to the minus x plus positive 5 times e to the minus x. And of course, we can easily see here that the left side and the right side end up equaling each other. And I don't know why I wrote not equal to. So we see those are equal. So yes, we know that this function y equals to e to the minus x is a solution to this first order differential equation. All right, so now we're going to check out the same thing, but we're going to do it with this function y that has 2 terms. So again, my y prime would be minus e to the minus x, and plus, we take the derivative of e to the minus 5/3 x. That would be a minus 5/3 times e to the minus 5/3 x. And then we'll substitute that in. So we have 3y prime plus 5y. Does that equal to 2 times e to the x. So we just substitute in. So y prime is going to be this minus e to the minus x minus 5/3 e to the minus 5/3 x, and then plus 5 times our original function. And again, does that equal to 2e to the minus x. So if we distribute this 3 to both terms, then we'll have a minus 3e to the minus x. 3 times 5/3 is just 5. So we'll have a minus 5e to the minus 5/3 x. And then we'll distribute to both terms there. And that will give us a plus 5e to the minus 5x plus, we have 5e to the minus 5/3 x. And again, does that equal to 2 times e raised to the x. From here, we see that this minus 5e to the minus 5/3 x and this positive 5 times e to the minus 5/3 x cancel to 0. And of course, what we have left here, if we were to combine like terms, would just end up being a positive 2e to the minus x. Okay. And so again, this is another situation here where we see that our function does indeed satisfy the first order differential equation. So for our last example here, we see that we have the profile very similar to the profile of this one, where of course the difference in between these two is that our value of c here is just a 1. So we can kind of take it here that this is actually going to end up also being a solution to the differential equation. And of course, if we worked it out, we would see that all that stuff would actually end up equaling on both sides of the differential equation there. So I'm not going to bore you with the details on it, but we'll just say yes, it will actually end up being a solution to our differential equation as well. Okay. All right. So we're going to go ahead and move on to the next example. So in the study of differential equations, a separable equation is one of the first type that you learn. The very first type that you learn is called directly integrable, and that looks something like, you know, what you see here, but I'm going to write something more along the lines of this. Okay, so this is what a directly integrable type of ordinary differential equation looks like. So of course here is directly integrable because I can take the antiderivative of my function that's on the right side of the equation without, you know, having to think much to do it. Okay. Now the difference in between a separable differential equation and one that's directly integrable is that we have this dy over dx is going to be equal to both function of y times a function of x times a function of y. Okay, so that's the big difference in between the two. And so because of that, because on the right side here we have a product of two functions where one is in terms of x and another one is in terms of y, we could technically rewrite this equation this way. Okay, and so by doing that, what we've done is we've actually separated the terms that have y variables in it with the terms that have x variables in it on opposite sides of the equation. So whenever we're able to do something like this, we call this a separable equation. And so this is the approach that we will actually take to solving this particular differential equation. Now, remember that the goal of a differential equation is so that when you solve it, you actually get a function out. So we are going to actually try to figure out what our function y is in terms of x from that. But the first step to do that is to get your equation from being in this form to being in this form here. And so after we do that, if I want to find out what y is, what I could do is integrate both sides. On the, of course, left side will be with respect to y. On the right side will be with respect to x. We'll get some function in terms of x on the left side, some function in terms, we'll get a function in terms of y on the left side and a function in terms of x on the right side. And then we just algebraically manipulate everything to solve for y if we can. Okay. If we can't, that's fine. We just get something that's simplified and it looks as good as it can look. Okay. Because sometimes the results that we get from these differential equations aren't going to necessarily always be nice, pretty functions. Okay. All right. So now that we've talked about that, I'm going to erase this and then we'll actually work out this problem. All right. So for this equation here, we see we have this function of x right here and function of y. So we just want to separate this so that all things in terms of y is on one side, all things in terms of x is on the other. So if I do that, I know that I can take this portion of the right hand side and I can divide both sides of my equation by that. And on the left side, I can multiply both sides here by dx. And when I do that, I'll end up getting just 2x times dx here. Okay. So now that I have that, the next thing that I can do is I can actually integrate both sides with respect to y on the left and with respect to x on the right. Okay. So if I do that, then of course the right-hand side is easy. The left-hand side depends upon whether you remember your inverse trig antiderivatives or not. Okay. So in short, what this ends up being here on the left-hand side, when I do this, this is going to be arc sine of y divided by 3 plus some constant. And actually, I'm going to do the plus constant on the right-hand side. And of course, here on the right-hand side, this is just going to be 2x squared divided by 2, because the antiderivative of x is just x squared over 2 plus some constant. And so if you're wondering, all right, well, how in the world did I get, arc sine? Well, I'll go over that once I'm done with the problem, just to make sure that you kind of understand where I'm getting that from. So needless to say, from this point here, these 2's will reduce to 1, and I will just end up having, and I'm going to write this as sine inverse form now. So I end up having this. And what I want to do next is take the sine of both sides. Okay. And so when I do that, I'm doing it with the understanding that the range of the domain of the inverse function is going to be the same as the range of the sine function. Okay. And so that's where this kind of comes into play. And I'll talk about that a little bit later too. So here we'll have sine of this. And then of course, whenever we do sine of sine inverse of something, we're assuming that this y divided by 3 here will actually be in the domain of sine inverse and in the range of sine. So that just ends up just being y divided by 3 equals sine of x squared plus c. And then from there, we just multiply both sides by 3. And we see that our function y is just going to be a function of x, and that function is going to be 3 times sine of x squared plus c. And that will be our final answer. And of course, our y values here will be in between -3 and 3. All right, so if you're wondering how we know that the integral of what we had on the left side of that equation ended up being arc sine of y divided by 3, well, we start off by knowing that in general, we know that the indefinite integral of 1 over square root of 1 minus u squared is just arc sine of u plus some constant, okay? So one thing that we can do here is, if I'm looking at, let's see, making sure I copy this correct. If we're looking at this situation here, one thing I can do is I can come here and I can factor out a 9. Okay, so if I do that, then I will have this situation here. And of course, I know from that point I can split this up in the denominator as square root of 9 times square root of 1 minus y squared over 9 in that term. And of course, square root of 9 is just 3. So I could write the understood 1/3 in the numerator. And in the denominator, what I would have is 1 minus y divided by 3 quantity squared. Okay, and I know that because y times y is y squared, and 3 times 3 is 9. So from this point here, I could say let u equal y divided by 3, which implies that the derivative of u with respect to y is just going to be 1/3. And thus, if I want to figure out what dy is going to be on its own, I would multiply both sides by 3, multiply both sides by dy, and I would end up having 3 du is equal to dy. And so now that I have that, I could take what I have here and now say that I have 1/3 times 3 du all over 1 over 1 minus u squared. Okay, and of course the numerator just ends up being du, and I just get this. And of course, when I integrate, I'm going to get this arc sine of u plus the constant, and then of course u is just y divided by 3, so that's why the y divided by 3 ends up in there. Okay. Now, if you're wondering why or how we even get that in the first place, meaning how is it that the arc sine of u is, and I take the derivative of it, is going to be 1 divided by square root of 1 minus u squared. I do have videos that you can check out on the derivatives of inverse trig functions. And so I go over that technique of actually using implicit differentiation to do that. So you can check out those videos to see how we actually know that this integral actually ends up being this particular function here as a result. All right, so I'm going to go back and we'll continue on with our next example. Oh, there was one other thing that I wanted to mention here. Yeah, sorry. So if you notice here that when we were at this point, notice that since this is square root of 1 minus y minus 3 quantity squared here, then what that does here is that it forces all of this to be greater than 0. And of course, if I go and work all this out, what I'm going to see here is that in order for this to be true, I know that this y minus 3 here is going to have to be a value that's in between 1 and minus 1, okay? And so as long as these values are in between 1 and -1, I'm good. And that's solely because, of course, I have this squared here. And of course, if I multiply both sides by 3, you see that my y value ends up being in between -3 and 3. So that is where this whole thing of y being between -3 and 3 actually came from. Okay. All right. So let's move on to our third example. Now, in our study of differential equations, one of the things that is well known is that anytime we have some kind of object or something that we're measuring, if the rate of change of it is proportional to itself, then we know that it follows the law of exponential change. And of course, that change could be either law of exponential increase or exponential decrease, depending upon the situation. So in general, how we look at that is we say, if we have the derivative of some function, and we'll say with respect to x, if that is going to be directly proportional to the function itself, so here's the function and here's some constant that is proportional to, then we know that in general, this outcome is going to be some function here, and I'm just going to write this in general. It's going to look something like this. So a function like a times e raised to the kx, and plus some constant there if we want to be specific. So my point here is that we know that exponential functions, if we take the derivative of them, they are proportional to themselves. Kind of like if I was to take the derivative of e raised to the 5x, we know that that's just 5e raised to the 5x because of the chain rule. Okay. So vice versa is also true. If I was to take the antiderivative of 5 times e raised to the 5x, then it would just end up being e raised to the 5x. Okay. So because of that, we know what the outcome of the solution to this type of equation is. In the problem that I'm going to do for you, I'm actually going to go through what that actually looks like when we do it. But in general, that outcome is going to look something like this. And normally we will leave off this constant here unless it's just absolutely needed. Okay. All right, so for example 3, we see that the intensity L of x of a light x feet beneath the surface of the ocean satisfies this differential equation that we see here. Okay, and so that equation just lets us know that the light beneath the surface or whatnot, how much of it we're actually going to see is following the law of exponential change, and in this case, exponential decay. We know from experience the diver knows that diving 16 feet in the sea cuts the intensity in half. And so in differential equation language here, we know that that's going to be the half-life, if we wanted to call it that, of the light. Okay. We cannot work with artificial light when the intensity falls below 1/5 of the intensity when at the surface of the sea. So that's the other piece of information that we're given. So we want to know how about deep can he expect to work without artificial light? So the first piece of information, which was this sentence, from experience, the diver knows that diving 16 feet cuts the intensity in half, that's given to us so that we can actually find our value k. The next sentence lets us know at what intensity level, or L of x level, are we going to experience to where at that point we're not going to be able to see anything. Okay. So, and what we need to do is find out the corresponding x value, meaning how deep are we whenever we reach this level here. So we have two things that we need to do. The first thing that we need to do is we need to figure out, well, what is L of x going to look like, and what is going to be this value k that goes along with it. So in short, we know that L of x is going to have to look something like this. And so I'm going to write this L naught just to say the initial intensity of the light, E raised to the, in this case, minus kx. And we'll just leave it like that. Now, the reason why this looks this way, I'll actually work through that once this problem is over, just for those of you that are interested in that. If you're not interested, or you already know, of course, you can skip that part. But I just want to, keep this reined in so that for those of you that are kind of already familiar with this, we can work out this problem. So once we're here, we know that when we're at 16 feet deep, the intensity is half. So that means when x is 16, we know that L of x is going to be 1/2 of what the initial intensity was. Okay. So what this tells us is that if I do 1/2 of what the intensity was here and substitute in my 16 for x, the only thing that I don't know here that I need to solve for is k. And so in doing that, if I divide both sides of my equation here by L naught, which is my initial light intensity, I'm just going to have 1/2 is equal to E raised to the minus 16k. And of course, from there, using logarithm properties, I can just take the natural log of both sides. That's one way I can handle that. And then, of course, this will end up being natural log of 1/2 equals to, and on this right side here, natural log is log base E. Log base E of E raised to the anything is just whatever that anything is. And then from there, I can divide both sides by 16 here. Or negative 16. So that is what my value of k is. I'm going to simplify this a little bit more. So here k now, if we look at the numerator, we can rewrite that as natural log of 1 minus natural log of 2 using logarithm properties. And we know that natural log of 1 is 0. And of course, that leaves us with a negative natural log of 2 over negative 16. A negative divided by a negative is a positive. So we are here. Okay. And so from here, I'm just going to write this as 1/16 times natural log of 2. And so that is what our value of k is. And so if we go and substitute this back into our equation for general equation for L of x, then of course the only thing that we won't know is the initial intensity, but we're going to see that we actually don't need to know that to be able to do this problem. Okay. So from here, we see that this L of x is now going to be L naught E raised to the, and now we're going to put minus and then write in all that stuff for k, which is going to be 1/16 natural log of 2, and all that times x, and all that's in the exponent there. Okay. And if I go and rewrite this some more, I know that I can rewrite this as E raised to the natural log of 2. And that part here, I can write the negative x divided by 16 on the outside, and I know E raised to the natural log of 2, that is just 2. So that is what my exponential function would actually look like for modeling the light. So now that we have that, the second piece of information that we're told here is that he cannot work without artificial light when the intensity falls below 1/5 of the intensity when at the surface, okay? And of course, the intensity at the surface is exactly what L sub 0 is. So what we know here is that now we're considering to find out what X is when L of X is going to be 1/5 of the original intensity of the light. And so in doing that, that takes our equation again, which in this case is this now. And we're going to set our L of X equal to 1/5 LO, and that's going to equal to L naught 2 raised to the minus X over 16. And so from there, if we divide both sides by L naught, we'll just have 1/5 is equal to 2 raised to the minus X over 16. And so from here, depends upon how you want to do this. Since my exponent has a base of 2, I'm going to use log base 2 of both sides. And so in doing that, this lets me know, of course, my left side is just going to stay as log base 2 of 1/5, but the right-hand side, log base 2 of 2 raised to the anything is just that anything. And then if I just multiply both sides by a negative 16, then I'll have negative 16 log base 2 of 1/5, and that will equal X. And so at this point, of course, I could simplify it some more, but we can just suffice to just type in the calculator at that point, and you'll see that we get roughly about 37.2 feet when we do that. Okay, so we know that the diver can only go a little over 37 feet. So we can only go over 37 feet before he can't, get light from the get light from it at all. Yeah. So he can work up to about 37.2 feet without the artificial light. Okay. Okay, so for those of you that are interested in knowing how do we actually get that L of X equation that we ended up with, we said L of X was equal to L naught, and here this was E raised to the minus KX. How we get that, I'm going to show that now. So note that per not our last example, but the one before it, where we were dealing with the separable equation, that this is technically a separable equation, okay? And here, if I was to rearrange everything, I could rearrange this equation to be the differential of L divided by L, and that's equal to K, negative K times dx, okay? And that happens by me multiplying both sides by dx and dividing both sides by L. So if I was to do that and then integrate, then of course on the left side, the answer to that would end up being natural log of absolute value of L. On the right side, we have a minus kx, because the k is a constant and the antiderivative of 1 is just x with respect to x, plus some constant. Okay. So from there, we could use our exponential rules that says that if I was to transform this equation here into an exponential equation using the same base, then I could do that. And since I'm dealing with natural log here, the ideal base to use would be E, because of the fact that natural log is log base E. On the left side, using our logarithm properties, we know that E, natural log of anything, is just that anything. And on the right side, we could write this as e raised to the minus kx times e raised to the c, using exponential rules there. Now, we see here we have absolute value of L, and we know that anytime we have an absolute value equation, we know that that means that what's on the inside is going to be plus or minus what is on the right-hand side. And so I'm going to switch the place of the e to the c and the e raised to the minus kx for that. We know that c is a constant, although we don't know what it is. We know that e is a constant, and we do know that that's an irrational number. So all of this together is working to be just some constant. And so from there, we could call that constant L naught. And then from there, we see that the rest just kind of comes together here. Well, this L naught here is going to be a plus or minus e raised to the c. And it really does depend upon the value of x and its corresponding L value to know whether that's going to be a positive or negative value for the initial, for that L naught, in this case, which is the initial light intensity. So that's how we actually end up getting that particular equation as a result of that differential equation that we were given in the problem. All right, so let's move on to the last example. So for this last example, we suppose that we have the bacteria in a colony grow unchecked according to the law of exponential change, okay? And in this case, since it's bacteria growing, that's going to be exponential growth. The colony starts with one bacterium, and the colony doubles in size every 15 minutes. So when we get that information about when it doubles, that's giving us the double time. And so we're going to use our differential equation to figure out exactly what that means in terms of the growth constant K. And so we want to know how many bacteria will the colony contain at the end of 24 hours. Okay. So the first thing that we want to do is note that since this is going to be following the law of exponential change, and I'm going to let the number of bacteria be population here, we know that the rate of change of population with respect to time is going to be directly proportional to the population itself. Okay. And so, by the way, whenever someone says, hey, this certain thing is growing at, let's say 10% or 5%, that's also another way of saying that it's growing exponentially. So it'll also follow this particular type of equation as well. So from here, we know that if we were to actually solve this, my function with respect to time would look something like this. Okay. And so we know here that our K in this case is going to be greater than 0. And it's going to be exponential growth. So that's why we don't have the minus sign here by the K. And we just need to use this to be able to figure out what is going to be our value of K, because once we have that, we'll pretty much have everything else we need. Okay. We know that the initial amount of bacteria is just 1. So we'll have that. And so with that, that's pretty much all we need to know to be able to solve for K. So let's go ahead and do it. Here, I'm going to define time in terms of hours. Okay. And I'm doing that because I have to figure out how many bacteria will be in the colony in 24 hours. So what that means here is that this 15 minutes, we know 15 minutes is 1/4 of an hour. So I'm going to refer to minutes in terms of hours here. Okay. So here, when T is equal to 1/4 of an hour, we know that the population is going to be 1/2 of what it originally was, which in this case was just 1. Oh, sorry, I'm doing 1/2. That should be double. So the colony doubles. So it should be double what it was before. And of course, I could say that this is going to be, if I was going to be technical here, I would say that this current population is going to be twice times whatever I would initially have. But since I already know it's 1, that's why I'm just plugging in 1 there. Okay. And so because of that, I know here that my P of t, which is the same as this P here, that's just going to be 2. My P of 0 is going to be 1. And so I'll just multiply that times e raised to the k. And my t now is going to be 1/4. Okay. So now all I need to do is solve for k. So again, using the fact I can take the natural log of both sides. On the left side, that will remain the same, but the right side, I know that that's just going to be k divided by 4. And if I multiply both sides by 4, I will get that k is equal to 4 times natural log of 2. And if I would use my logarithm property that says that anything multiplied times a logarithm is the same as the exponent if I put it on the inside, I know that my k now is just going to be a natural log of 16. And again, I'm taking that extra step to do that just to make the math easier for me later. So therefore, I know that my population for the bacteria is just going to be e raised to the natural log of 16 times t. Okay? And if I rewrite that using my exponential rules, note that I can also view this way. And I know that e raised to the natural log of 16 is just 16. So P of t is simply just 16 raised to the power of t. And so now that I have that, to find out how many bacteria will be in the colony in 24 hours, well, that's pretty simple. Because all I have to do now is plug in 24 in for t. And when I do that, and this is just an approximation here, I'm going to get a large number, but the number is essentially just going to be 7.9228 times 10 to the 28 bacteria. Of course, if we were doubling the size every 15 minutes, we do expect that to be a lot. Okay. All right, so with that being said, that concludes this example and this video of the light introduction to differential equations. I hope this helped. Take care.